All right. Good morning, everybody. Welcome back. So for this week, let's start where we left off on Friday. So let me share my screen with you. Okay. Some important announcements for this coming week. First, we will have in-class assignment this coming Friday. I will talk a little bit more about the format of the assignment on Wednesday. Okay. Don't forget that you have online homework for chapter 1, part 1 due on Thursday night. So again, don't leave it for the last minute. Give yourself time to complete the assignment. And today we will have our first discussion session. So for the discussion, I will post the problem set on Canvas before the discussion starts, and I will be available on Discord if you have any questions regarding the problem set, okay? And of course, you are more than welcome to discuss with your colleagues if you guys have any questions as well, or if you just want to double check your answers. And then don't forget to submit your answers on Canvas as well. Okay, so we need to talk about two more topics to finish chapter number 1. And hopefully we'll cover everything today and start chapter number 2. Okay, so let's start with conversion between units. Conversion between units is a very, very, very important thing to know in chemistry, and you need to be sure that you understand and that you know how to convert any kind of unit, okay? So in this course, if you don't understand something, make sure you ask questions and you understand, because it will come back and haunt you later on in the semester, okay? So we need to know all the steps that we are covering here. Okay, so to convert between units, you have two different ways. The one I like is by using proportion, or you can also use dimensional analysis and conversion factors. So let's get here as an example. I need to convert 40 feet to meters. And you know here that 1 feet is equivalent to 0.3048 meters. So the way I will show you how to do it is by using proportion, because I think it is easier. But you are free to use whatever you want. Okay, so let me switch to my other screen that I can write. Okay, very good. So first thing here that you need to observe is that I provided you the conversion factor. Okay, so if I don't provide you the conversion factor, you need to look up for it. All right. So now that I know the conversion factor, what I'm going to do is to write two different columns. The first column will have the feet information, and the second column will have the meter information. And remember, I need to transform feet into meters. The first line of my proportion is always the information that I know, okay? And the information that I know is right here in the conversion factor. So I know that 1 foot is equivalent to 1 meter. Sorry, 0.3048 meters. And that's going to be a fraction. The second line will have the information that I want to know. I want to know 40 feet is equivalent to how many meters, okay? So it's an equality, okay? So that means the left side must be equals to the right side. So to solve that, you can do a cross multiplication. So you're going to end up 1 foot times x equals to 0.3048 times 40. Therefore, this conversion here will yield the number, according to my calculator, 12.192. Okay, so doing proportion, you are going to be able to solve any kind of conversion problem and later on any stoichiometry problem with chemical reactions. And look, there is an equal sign, right? So whatever happens on this side needs to happen on the other side. If one side was multiplied by 40, the other needs to be multiplied by 40 as well. So you don't need to do many calculations to figure that out. Okay, and so we have 12.192, which was the result that the calculator gave us. However, we need to express this result with the correct number of sig figures. So we have multiplication and division here. So therefore, we cannot have in our result more sig figs than the lowest sig figs in the numbers that participate in the operation. However, every time you have a conversion factor, that is considered an exact number. So this here is an exact number. Therefore, we do not count anything from the conversion factor for the sig figs, okay? No participation in the sig figs. So any number from the conversion factor will not participate in our decision for the sig figs. Therefore, the only number that will limit our significant figures is 40.0. 4 is significant. We have a 0 and a decimal point, so that's significant. And the last 0 is significant as well. So we have here 3 sig figs. Therefore, our result must have 3 sig figs. 1, 2, and 3. Chop here. We need to round this number. So we have a 9 after the chop. So we are going to exclude it and add 1 unit. So therefore, we have here 12.2 meters, and that's the best way to express your result. Okay, so all the things that we've seen before, it will start coming together, okay? And you need to know what was covered before. Okay, very good. Let's cover our last topic for chapter number 1. So let's talk about density. So density, represented here by D, is simply the ratio between mass and volume. Okay, very simple formula. Units in the international system, mass is in kilograms and volume is in cubic meters. So therefore, the unit for density in the international system is kilograms per cubic meters. Remember that I can move cubic meters to the top in exchange to changing the sign of the exponent. Okay, so kilograms meter to the -3. That's also a way to represent the unit of density. To observe density, we don't need to change any of the chemical composition of the system. So therefore, density is a physical property. And is it extensive or intensive property? Extensive depends on the amount of substance that we have, and intensive does not. Okay. So if you get a small piece of wood or a large piece of wood, they have the same density because that's a characteristic of the material. So therefore, density is an intensive property.
Wait, why is it an intensive property again?
Because intensive properties, they do not depend on the amount of substance that you have or amount of material. Okay, so if you get a small piece of wood or a large piece of wood, they will have the same density because that depends on the material. So therefore is intensive. Okay, awesome. All right, and so you can actually do this experiment. So fill a bucket with water. If you have regular Coke, it will sink down to the bottom, and Diet Coke will float on the surface of the water. So why do you observe that? Okay. So the can has the same volume. However, when you have regular Coke, you have sugar added, right? And the biggest difference between regular and Diet Coke is sugar. So here you have a lot of sugar, and here you have just a little bit of sugar. So therefore, the mass of the regular Coke for the same volume is higher, which means higher density. So that's why the regular Coke sinks down to the bottom and the Diet Coke goes up to the surface. Okay. So with that, you can actually open the can and start adding sugar until you observe this can going down to the bottom. And that's exactly the amount of sugar that the regular Coke has. Okay. So you would be surprised how much sugar you need to add here to get this to sink down to the bottom. Emily, it depends on the alcohol. Um, Usually, yes, they are less dense than water. Okay, very good. Okay, awesome. So with that, let's start the next chapter. Get here, chapter number 2. Okay, let's go to chapter number 2. Okay, so starting here, chapter number 2. So now we will start covering a little more in depth of chemistry. For chapter number 2, we will start covering atomic models, talk a little bit about periodic table and electron configuration. So attention here that I'm bringing some topics from chapter number 7. After that, we will discuss average atomic mass and isotopes, trends in compounds formation. So we will see 2 classes of compounds and bringing up some topics from chapter number 8. And finally, we will go over formula and nomenclature of some inorganic compounds. Okay, so this last topic here will require a lot of practice, and we will try to do as many exercises as possible. Okay, so let's start talking about atomic models. Models, in general, relate the uninspectable thing, meaning too small or too big, either to familiar things or to abstract mathematics. Okay, so when you have a very small thing that you cannot manipulate, you are going to create a model to relate that to something that's familiar to you and something you can manipulate. And the opposite is also true. If you have a too big of a system that you cannot manipulate as well, you are going to correlate this with something that's familiar to you. The use of models allows to delve even deeper in nature's secrets and harness via technology forces not previously available to us, and always develop better models by building on points 1 and 2. Remember that a model is never 100% accurate. Okay, so we always going to do experiments to prove or contradict the model, and with that information we can build on a better model. Okay, so let's talk about the atom. The first ideas of the atom were developed in Greece by Democritus, okay, in 460 before Christ. And what Democritus proposed was that, okay, so if we start with a big chunk of clay and we cut this in half, then cut again, cut again, cut again, and etc., 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 we are going to get to a point that we cannot split this particle anymore. And that small particle was the atom. Okay? So according to Democritus, there would be a point where the matter could not be divided anymore. And this particle was called atoma. And it is the building block for all matter. Okay? So for Democritus, atom was the smallest particle possible, and it was the component of all the matter that you can have. Okay, so the idea of Democritus actually survived for a long time. Um, and the next important atomic model after Democritus is the Dalton atomic model. So Dalton developed his atomic model in the beginning of the 19th century. And for Dalton, all matter is made of atoms. So still the Democritus concept was kind of correct. Second point, atoms are indivisible and indestructible. Third point here, all atoms of a given element have the same mass and properties. So therefore, the mass of an element was the characteristic of the element. Okay. Compounds are formed by a combination of two or more different kinds of atoms. And fifth point, a chemical reaction is a rearrangement of atoms. Dalton was one of the first scientists also to propose symbols for the different elements. Okay, so very artistic here. Have these circles here with some very nice drawings inside. And on the right side here of each column is the mass of each element that was known at the time. Okay, so let's think about these 5 points for a minute. Think which one you think is still true today and which one is not true anymore. So think about it. You don't need to answer me. Okay, so let's see here which of the statements from Dalton is still alive today. All matter is made of atoms. That's very true. Atoms are indivisible and indestructible. So that is not correct. You can divide an atom. So that's what happens when you have a nuclear reaction. Okay, so statement number two is not true. All atoms of a given element have the same mass and properties. That's not correct. What characterizes an element is its atomic number, not the mass, okay? And you can have the same element uh, with different properties. That's what we are going to see on the isotopes. Compounds are formed by a combination of two or more different kinds of atoms. Okay, so that's not correct. You can have a compound formed by the same kind of atom. For example, oxygen gas is formed by oxygen bonded to oxygen. So you don't need different kinds of atoms. And fifth, a chemical reaction is a rearrangement of atoms. That's correct. Okay, chemical reactions are basically rearrangement of atoms to form new compounds. All right, considering the technology that Dalton had in the beginning of the 19th century, his model is not bad at all. Okay. Okay, so Dalton atomic model was important to establish a floor, and with that floor, then we can move on to better atomic models. Although initially successful, the Dalton atomic model could not explain the nature of the fluorescent rays generated by high tensions applied in glass tubes at low pressure. And those fluorescent rays that we observe in these conditions are called cathode rays. Okay, so what happened with the cathode rays that the Dalton atomic model was not able to explain? So let's see here a series of observations and see the consequence of each observation. Observation number one, the rays were generated independently of the material used as the cathode, or the metal plates over here, or the gas inside the tube. Okay, so whatever were the rays, they are part of the composition of all matter. Second observation, the rays were attracted to the positive pole of the plate here. So if the rays were attracted to the positive pole, the charge of the rays are negative. So therefore, we have something that is part of the composition of the matter, okay, so part of the atom. It has negative charge. Let's see here with what the observation number three tells us. The ratio mass over charge for the cathode rays is smaller than the one for the hydrogen, which is the smallest element found in nature. The consequence of that is that the rays are smaller than the smallest atom. So therefore, we have something that is present in the composition of the atom. It has negative charge and it has a very low mass. Other observations, the rays produce shadows and can move a petal. So therefore, they have a dual wave particle nature. So we will tackle this later on. So let's work with these three observations here and consequences. And let's try to figure out what the cathode rays were. So for that, we will bring on the Thomson atomic model. J.J. Thomson's research group extensively studied the cathode rays. His research group found mass over charge ratio 1,000 times smaller than that for the hydrogen. So therefore, Thomson came up with his own atomic model, and this is also known as plum pudding model. And according to Thomson, the atom is a sphere of positive electrification, and inside this sphere, a number of corpuscles arranged in a series of parallel rings, the number of corpuscles in a ring varying from ring to ring. Okay. So therefore, this atomic model, the consequences of Thomson atomic model were that first, there are smallest particles than the atom. These small particles have negative charge. Later on, they were called electrons, okay? There were huge implications for the development of magnetism and electricity, and there was some loose connection here with a periodic table in a sense that each element will have a different amount of electrons. Later on, Millikan determined the charge of the electron and therefore its mass using the mass charge ratio determined by Thomson. So you can see more details on page 50 of the textbook. And therefore, the conclusion was that electrons are light and most of the mass of the atom's mass is diluted throughout the atom, okay? So now the biggest difference here between Thomson and Dalton atomic model is that for Dalton, we have the atom as this solid sphere. On the other hand, Thomson figured out that, okay, so first we have a smaller particle than the atom, which is the electron. The mass of the atom is diluted throughout the atom, and we have electrons kind of encrusted in this jelly kind of atom here talking. Okay, so the biggest difference here is moving on from a solid thing to a more fluidic thing and figuring out that the atom is not the smallest thing we can have. Okay. Okay, so now that we have this new Thomson atomic model, Next step here is to test the model to see, to figure out if this is a good model that's going to explain everything, or if we have any flaws and we need to adjust the model. Very simple experiment here. We have a sheet of gold right here, and around it we have a fluorescent screen, and we are going to shoot alpha particles through the sheet of gold. Okay? So alpha particles are very dense particles, and when they hit the fluorescent screen, you are going to see a spot. So therefore, you can track where these alpha particles are going after passing through the sheet of gold. So according to the Thomson atomic model, the mass of the atom is diluted throughout the atom, and we have these very light negative particles encrusted and diluted throughout the atom. So imagine here that we have a sheet of paper, okay? So in a sheet of paper, the mass is not concentrated in one spot, but diluted. So we are going to lay this sheet of paper flat on the table, and we are going to roll some ping pong balls throughout the sheet of paper. So what you expect in this case is that all the ping pong balls will pass through the sheet of atom without any problem, right? Because there is barely a barrier there for that. However, when we run this experiment, okay, most of the particles pass through the sheet of gold without problem. However, some particles, they seems like they hit something very dense and come back, okay? So because some particles came back, this explanation here is not valid anymore. So therefore, we have to figure something out to explain this huge deflection here. So now imagine that I get this sheet of paper and I make it into a small ball. So now I'm bringing all the mass and concentrating it in a small volume. And I run here the same experiment, okay? So now we have a lot of empty space, and most of the ping pong balls will pass through that without any problem. However, some of the ping pong balls will hit the top of this small ball of paper and get deflected, and some of them will hit right on the ball and they will come back, okay? So this model here, now all the mass concentrated in a small volume matches what was observed in the experiment, okay? So therefore, that tells us the Thomson atomic model needs to be improved, and we need to bring on a new atomic model. And now it's a good time to present the Rutherford atomic model. Rutherford was a student in Thomson's research group, and he was able to come up with a better atomic model. For Rutherford, now we have a small nucleus where most of the mass is concentrated and electrons are moving around the nucleus. Okay, so now the biggest change from Thomson to Rutherford is that The nucleus is small, very dense, and most of the mass of the atom is in the nucleus. Consequences of the Rutherford atomic model. First, we have positive charge concentrated in a small volume called nucleus. Second, the electrons are moving in orbits around the nucleus. Okay, so therefore, for the first time, we have two different regions in a atom. The first one is a very small volume, positively charged, and most of the mass is in there, which is the nucleus. And the second part of the atom is very light, has negative charge, and is composed by the electrons. Okay, so this is a good point for us to stop for today. So I will see you guys during the discussion section and then later on Wednesday. Okay, so bye-bye. I hope you have a good week.